Hi everyone, welcome back to another tutorial. Today we're going to go over question 1 of a paper on standing waves, and then in another video I'm going to go over diffraction and interference. Okay, so question 1, we've got a plan flute. It's a wind instrument that creates sound when air is blown across it. It consists of linked pipes that are bound together. So here's the important information that I care about. Each pipe is closed at one end and open at the other end. So it's a closed pipe, which means it will only have a quarter wavelength harmonics. In the diagram below, draw a diagram of the third harmonic that can be produced. And then you also have to label the nodes and antinodes. So the third harmonic is just going to be 3 times of the fundamental frequency or the fundamental first harmonic. So it's going to look something like this. Okay, so this to there is roughly half the wavelength, and then this bit here is the quarter. Because remember, we want 3 times a quarter because it's a third harmonic. And then you can draw the dotted line as well to show that sort of reflection of itself when it interferes. So obviously for closed ends, it's always going to be a node, and then for open ends, it's always going to be an antinode. So we're going to have a node here, and then we're going to have an antinode in here where there's the maximum displacement or a maximum gap. We're going to have another node here in the middle, and then we're going to have another antinode right at the end, right? So anything that sits in the middle, I'll draw another middle line. Actually, I'll make it green. Anything that, I'll redraw that. Okay, like this. I'll just redraw this green line. So, next question. Jan has a pan flute. The shortest pipe is 8.5 centimeters long, so we need to change that to meters. Okay, calculate the frequency of the third harmonic produced in the shortest pipe. So we're concerned about the shorter one. So the frequency formula is this here, where if we rearrange, it's going to look like this. So the velocity of the wave, they usually give it to us. It's up here, and it's usually always 343. So we've got V, but we need the wavelength. We don't have the wavelength, but we can find that length of the pipe. So in a closed pipe, L equals a quarter of the wavelength, right? So wavelength is going to equal to 4L. When I move the 4 to the other side, I'm timesing it by the reciprocal. So 4 over 1, which is just 4. So my wavelength is going to equal 4 times the length of the shorter pipe, which is 8.5, but we've got to convert that to meters. So that's going to be 0.085. And if you put that into your calculator, you should get an answer of wavelength equals 0.34 meters. So now we have the wavelength. We can go F equals 343, which is the velocity of the sound wave, divided by 0.34. And if you do that into your calculator, you should get an answer of 1008. Now, what we've found here is not the third harmonic. It's actually the first harmonic frequency. So we need to multiply this by 3. So F3 equals 1008 times 3. And if you do that, you should get an answer of 3026. And then you can just round that to 3030. Okay, and that is a merit question, by the way. And the one before was an achieved question. Okay. Part C. Explain how standing waves are formed in a pan flute that is open at one end and closed at the other end. And explain why not all harmonics can be formed. Okay, I'm going to write this down and then explain it. Okay, so I've written out the answer to this question. It is a pretty long excellence question, but I'll break it down bullet point by bullet point. So the first thing you need to address is how standing waves are formed in the pipe. That's part one. And in part two, you need to explain why not all harmonics can be formed. Now, this is a very common question. So first of all, you should start by saying standing waves form when sound waves travel in the flute and reflect off the ends and interfere with itself to form nodes and antinodes. Second point you need to have is waves at the open end reflect in phase. That is really important, which means it will constructively interfere, which forms a permanent antinode at the open end. So those three things. This is the complete opposite for waves at the closed end. They're going to reflect 180 degrees out of phase, which is destructively interfering, forming permanent nodes at the closed end. Pipe, only odd multiples of a quarter wavelength produce a node at the closed end and an antinode at the open end to resonate, producing a standing wave. So that's why you can only have the first harmonic, third harmonic, fifth harmonic, F1, F3, F5, because they are odd multiples of a quarter wavelength. If you had the second harmonic, that would be an even multiple, because a quarter times a quarter is a half, right? You cannot have the second harmonic or even numbered harmonics, as these produce multiples of a half wavelength, which have nodes at both ends or antinodes at both ends, because if you have a half wavelength, it will look like this, which has a node here and a node here, which is not, it does not work in a closed pipe. It exceeds the physical limitations of a closed pipe because you must have a node and an antinode at the other end. So that's that question. This is a pretty big excellence question. To get excellence, you needed to have explained both points. So write E is everything. A mirror is you explain one of them well. So you either explain how the standing waves are formed or you explain why not all harmonics can be formed. So M is one well explained. And then achieved is just describing one of them partly. So waves reflect and interfere, or waves are in phase, which produce an antinode. Just any little minor point. So any minor point. Okay, the last question for standing waves. Some pan flutes, blah blah blah, can be tuned. Alright, that word tuned is quite important because straight away that's telling me it's got something to do with beats, which you might have not learnt what beats are yet, but I can explain it really quickly. Inside the pipe to adjust the length. Okay, so we're changing the length. That's also important because if we're changing the length, we're also changing the wavelength, okay? They're proportional to each other. Initially, the length of the longest pipe is too long and the untuned pipe creates a beat of 9 Hertz with another tuned pipe. Okay, so that's our beat frequency, FB. I'm just going to write the formula down on the side. FB equals the absolute value of F1 minus F2. These are the two frequencies of the two pipes. The tuned pipe has a length of 0.164, which produces a frequency of 523 when playing the first harmonic. Calculate how much further the cork needs to be pushed into the pipe and explain how it is possible to hear when the cork is in the correct position. Well, you know it's in the correct position when you have a beat frequency of 0, because that means the two frequencies will be the same. So I'm just going to draw some sketches out and do the calculations and explain some stuff. Right, I thought I'd carry out the calculations because it is quite complicated, but I've drawn some stuff that may help. A quick diagram for these word questions is really good because it's a lot to sort of take in. So you want to sort of lay out your key points really clearly. So the untuned pipe we know is longer. We don't know the length of it. That is what we actually need to find. So we need to find the length of it. We are given the length of the tuned pipe, which is 0.164 meters. We're also given the frequency of the tuned pipe, which is 523. But we don't know the frequency of the untuned pipe yet. But they have given us the beat frequency. So because we know the untuned pipe has a larger length because it's longer, that means it's also going to have a larger wavelength. So that means its frequency has to be less than the 523. So when we go to our formula, we know FB equals 9. F1, we know it has to be the 523 minus F2. 9 minus 523 is going to equal F2. By the way, F2 is the frequency of the untuned pipe. So that's F2. And then F2 is going to equal negative 514, but we absolute value it, so it's actually just going to be 514 hertz. And that checks out because it's supposed to have a lower frequency than the tuned pipe, which is F1. So now we've got the frequency of the untuned pipe. We can now work out what the wavelength is going to be. So we've got our V equals F lambda. I can rearrange for the wavelength. Now the velocity is still going to be the 343. That's not going to change. Our frequency is what we just found, F2, so 514. And doing that, you should get a wavelength of 0.6673 ... meters. Now, we can use this wavelength to find the length of the untuned pipe. So we know the length of the untuned pipe equals a quarter of the wavelength for a closed pipe. So, L, oh, it's not letting me. Okay, so you're going to put that wavelength in we found. So it's going to be a quarter times this here. And that should give you a length of around 0.1668 ... meters. So this, what we found, is the length of untuned pipe. So if I do my little diagram sketch again, this is that 0.1668 that we just found, and the shorter pipe is the 0.164. Okay, it's up here. We need to find how much further the cork needs to be pushed into the pipe so that it's in the correct position to have 0 beat frequency. So basically we need to find how much this distance here is, because that's how much the cork needs to be pushed through to make them equal in length. Because we're now the same length, same L equals same wavelength, which gives the same frequency. So you're going to have 0 beat frequency, which is what we want. So it's going to be the 0.1668 minus the length of the shorter pipe, 0.164. That's going to give you an answer of 0.0028 meters. Right? So that is how much we need to push the cork in to where we're going to have 0 beat frequency. So as the cork gets pushed, the beat frequency is going to get less and less and less. So when L decreases for longer pipe, beat frequency decreases until FB equals 0.